As promised with a previous short, we're going to show you how to calculate morphs, and it's something that's very easy and anybody can do with just their fingers. Our special guest for that short was Teddy, who is a ball python, and he has black pastel, red stripe, yellow belly, and fire. So how do we find out what our little buddy might have expecting for children if we were to breed him with, well, hopefully another ball python? This is the Reptile Information Review. So as we watch this technique, maybe one question would be, but does it work on recessives? And of course it works on recessives. They pass down pretty much the same way. Let's talk about genetics for a little bit so that we can kind of follow along with exactly what the theories are behind this and how this all develops into something that you can do counting on just your fingers. So the two examples that we've already seen are ball pythons, but this works across any species that have what are known as Mendelian traits, which is pretty much everything. But just to be clear, that means your corn snakes, your sand boas, your rats, any of it. When we look at ball pythons, they're a really great example of inheritance because they have so many different morphs or phenotypes or expressions of different genes. Mendel, when he was observing through these breeding projects that certain traits were passed down from the parents, and it was pretty much random which parent it would come from. That's kind of what we're working on when we see people draw out the Punnet squares, which is the little squares, and then they use, magnets or a piece of paper or thumbtacks or Sharpie markers or whatever they're doing. So a Punnet square is a way to visualize exactly what I'm about to tell you. And don't worry, there'll be some more examples later. I'm sure somebody's going to come up with, well, what if you have 7 different recessive? It still works. It's still exactly the same. So first, to run over the basic concepts, is we're talking about, Mendelian traits. So Mendelian traits are traits that are inherited through the observations that a man named Mendel made a very long time ago. Look it up on Wikipedia. It's like 3rd grade genetics, right? But as I said, we're going to do it with just our fingers. We're not going to use any other props or any other calculators or anything like that. So Teddy, which was our example, was yellow belly, red stripe, fire, and black pastel, right? So we know that the base type is going to be normal. There's no supers in here. There's no visual recessives. There's nothing like that. So with the base type as normal, each gene has 50% chance to be passed down. Of the 50% that gene passes on to, each other gene is an additional 50%. Okay, that might sound a little bit confusing. So this is where, there's no wrong way to do this. They're all exactly equivalent. So if you want to think of it in fractions, 1/2, 1/4, 1/8, 1/16, you can. If you want to think of it in percentages, so 50, 25, 12.5, 6.25, right? However you want to think of it, 1 in 8 chances, whatever it is, it's all going to be exactly the same. Personally, the way that I usually think about it is in powers of 2. This is just different people are different, right? So if we use our powers of 2, we've got 2, 4, 8, 16. So I know there are 16 combinations of the genes inside that snake, and 1 in 16 will be a snake exactly like him. I know that 1 in 16 could be just yellow belly. 1 in 16 could be just fire. 1 in 16 could be yellow belly, fire, black pastel with no red stripe. That's the total number of combinations that there could be. And the odds of you getting it are just as equal as the odds of getting any other combination, whether that's 1 gene or all 4. This works exactly the same with recessives. And it's only slightly different when it comes to things like allelic or ALS or however you want to term it. So again, on just your fingers, we're going to go over it again, and we're going to go through it a couple different ways. Again, they're all identical. It doesn't. The math is the same, but some people just prefer to think of things in different ways. I like to think of it in power of 2s. Somebody else might prefer fractions. So when it comes to fractions, you would do half. Half divided by half is 1/4. 1/8. 1/16. That's 1 in 16, however you want to refer to it. So that would be the fraction way to do it. What's next? Percentages. Then you could do 50, 25, 12.5, 6.25. If you wanted to do your powers of 2, you've got 2, 4, 8, 16. That's all there is for 4 genes. If there were only 2 genes, then you would only have to do 2, 4, or 1/2, 1/4, or 50%, 25%. It's all the same. When we get into our recessives, the only thing that we're really going to change is the base type. So if you have a visual lavender albino and you have a het lavender albino and you want to combine them, your base type, no matter what, will always be het lavender albino. A visual will always produce 100% hets. Now, of those 100% hets, 50% will inherit the other side of the lavender albino from the het lavender albino, and that'll be your visual chance. So let's look at it. If we look at it again and we say, okay, our base type is het lavender albino, and we have one gene being passed down from the other partner for the snakes, that one would be het lavender albino. So we look at it, and again, however you want to look at it, you've got your half, your power of 2, your 50% will be visual. If you want to continue to stack genes, don't worry, I've got some slides that we can get as complex as you want to get with it. The same way that we would do recessives is how we would do supers. So if you started with let's go with super inchy, then we know our base type will always be inchy. If we went ahead and added, let's go with bamboo, right? So we know our base type is inchy and we add bamboo. So 50% of those animals will be bamboo inchy, and the other 50% will be our base type, which is only inchy. And you can continue stacking genes like that. You can add recessives if you want to. This also works the same way with allelics, or ALS, or however you want to say it. So if we did chocolate spot nose, and we bred a chocolate spot nose to an inchy, then we know that inchy, our base type, of course, is chocolate spot nose. Inchy will be passed on to 50% of those animals. Since chocolate and spot nose are allelic, one or the other will always pass down. So we know half of those will be chocolate, half of those will be spot nose. Using just those basic powers of 2, all of them are the same. So calculating acts like super, calculating, or ALS, or however you want to say it, or allelic, or visual recessive, or het recessive, or simple incomplete dominant, all the same. It's all identical. So since some people will probably benefit a little bit more from reading this, we're going to go ahead and run through some calculations. Good old PowerPoint, right? So the most simple example, we're going to use inchy again. This is an incomplete dominant, and our pairing is going to be normal and inchy. There are no supers, recessives, or anything like that in this example. As mentioned, base is going to be normal. So using my method that I like to use is 2 to the power of 1. So that's 1 and 2 are going to be inchy. I'm done. That's it. That's all there is to it. Let's get a little bit more complicated. So if we went ahead and used 3 different genes this time, so we've got pastel, leopard, and inchy. Once again, our base is normal. There's nothing special in there that is going to change, that we're still going to get normals. If we use, my good old method, powers of 2, we've got 2 to the power of 3. That's 3 genes. So 1 and 8, you can keep dividing your halves to get 1 and 8. You can do your percentages, whatever you want to do, and you can see at the bottom that we've got all of them listed out, all of the different combinations. So that one's not too tricky. We know that the jackpot, or probably the most desirable, would be that inchy leopard pastel, and you have just as good a chance of getting that as you do probably the least desirable, which would be normal. We talked about supers briefly already, so let's get crazy with this one too. We're going to go ahead and throw 3 genes in there. Well, technically 3 genes, 2 different genes. But so one's going to be super inchy. The other one's going to be bamboo inchy. So our base is going to be inchy. So this is different than the other examples since we are working with a super. We are 100% guaranteed that every snake in this clutch is going to be inchy. What we're not guaranteed of is the other bamboo and inchy. So those are going to be 50% chance of being passed down to the offspring. So 2 to the power of 2, 1 and 4, divide, whatever you want to do. And what we'll find out is that we've got 25% chance at super inchy bamboo. And then, of course, 25% chance at just inchy. As mentioned, recessives aren't really different. So if we did normal in ball python, let me try that again. So if we did normal in piebald, then we know our base is going to be het piebald. Easy enough. That's all there is to it. If we did a het piebald and bred that with piebald, then we know that the base is going to continue to be het piebald from one parent, and the other parent has a 50% chance of passing in either the piebald gene or what would be normal or wild type, or however you want to say it. So again, our base is het piebald, and 50% of those babies are going to be bright white. Well, maybe. Who knows? What else? Depends on what else you have in there. Now let's get really crazy. So if we did a piebald het lavender and bred that with an inchy lavender het piebald, we have a couple different things going on here. So because of the piebald in one parent, we know that our base is going to include piebald. And because of the lavender in the other parent, we know that our base is also going to include het lavender. So in this case, we've got double het lavender and piebald. We can just move those genes to the side because they're guaranteed and they're outside of our probability calculations. These are 100% going to be present in all of these offspring. So if we just look at the core there, we only have 3 genes that we have to work with, even though that looks a little bit intimidating. So we'll cut it up again. So I'll do 2 to the power of 3. That's the easiest one for me. 1 and 8. So 1 and 8 would be our winner there. Our winner would be the piebald lavender albino inchy. We know that at least 50% will be visual piebald because it still works the same. If you look at piebald paired with het piebald in this example, lavender is identical. At least 50% will be lavender. And then 25% will be both piebald and lavender for dreamsicle. So we'll go and revisit our old example. If you've been following along this far, then you know that we've already covered super inchy times bamboo inchy. And by now, this should be super easy to look at and review in your head. If we jump back one previous slide, it's the same exact, it's identical. So whether you're working with recessives or if you're working with incomplete dominance, the rules are exactly the same. Allelics / ALS or acts like super or however you want to refer to it, we're going to use chocolate spot nose as our example again. We're going to do spot nose and chocolate, and we're going to breed that with a bamboo. So our base here, because of that combination of chocolate and spot nose, is going to be a spot nose or chocolate offspring. There's 50% chance of either one because both of those genes have 50% chance of being passed down, but both obviously cannot be passed down, only one or the other. And then of course we've got bamboo there. So bamboo is just the one, however you want to say it, the one wild card, the one that we're looking for the percentage of. So we know that 50% will be chocolate or spot nose with bamboo, and the other 50% will not have bamboo. They'll still be chocolate or spot nose, but they won't have bamboo. If you want to break that down even further, yeah, you can say that probability is 25% is bamboo chocolate, the other 25%, and you can break it all the way down to 25% if you want to. But if you're doing this, as again, this is to show you how to do it on your fingers. If you're doing it on your fingers, you can just kind of put chocolate and spot nose to the side and assume 50% of those will be one or the other. Now let's get really crazy. We're going to combine chocolate spot nose. So that's our allelic or ALS combo. We're going to combine clown, which is going to be our visual recessive. We're going to cross that with a super pastel. So we've got a super incomplete dominant there. And then we're going to throw a het clown in there. So we know that our base, looking at all of these, we have quite a few genes that are 100% chance to be passed down. So that pastel will definitely be in there. Chocolate and spot nose, chocolate or spot nose will definitely be in there. And then of course, het clown will definitely be in there. But ultimately, once we take our base, the only, wild card or however you want to say it, will just be the visual clowns. So again, demonstrated here is you can go ahead and split half to be chocolate, half to be spot nose if you want to, or you can just refer to it as 50% will be chocolate or spot nose, and the other 50% will be spot nose or chocolate, right? This has caused a silly amount of controversy. You see arguments about it way back on, I think it was ballpython.net. Somebody was arguing that the world of ball pythons wouldn't give the community their calculator. This calculator, this is math that has been available forever. There's an argument started on Morph Market's forums where somebody tried to say that Morph Market had some sort of intellectual property right and non-competitive to this sort of math. This is math. This is easy. That, of course, was not the Morph Market admin or owner, just to be clear. That was just some random on the internet that didn't quite understand how this worked. Of course, if you go to Facebook, there is an infinite number of geneticists that will tell people they don't know how genes work. Now you do. It's super simple. I showed you how to calculate it on just your fingers, and we even went through some very complex examples. So the next time that you're at a show or something like that, instead of taking out your phone and trying to figure out, well, if I brought this animal into my collection, just use your fingers. I mean, you've got 10 of them. If you're working beyond anything like that, I suppose you could use toes. But at the end of the day, as long as you can just keep track of multiplying by 2 or dividing by 2 or however you want to say it, any number of those genes will tell you the total number of combinations. All else fails. If you're really stuck, you can simply write out every combination that you know is valid. And at the end of the day, that is equivalent to any of the other methods that we've already talked about. Now, there is something to be said about the calculators that people create, whether that's, if you want to use more markets, that one's fine. World of Ball Pythons, that one's fine. The additional value that's added there is that you have developers that are going in and adding things like allelics, like chocolate and spot nose. So if you didn't know that chocolate and spot nose were allelic and you try to do these calculations, you're not going to get it right. The value add there being somebody should have already put all of that inside of a table.